In this video, we're going to talk about increasing and decreasing functions and the first derivative test. So if we let f be a function over an interval I, then f is increasing on the interval I if for every value a less than b in that interval, f of a is less than or equal to f of b. So if this is our interval I, then we would say that the function is increasing, and maybe that looks like that. It's increasing over that interval because for any points a less than b that we choose, f of a is going to be less than or equal to f of b. Similarly, f is decreasing over an interval, f is decreasing over an interval I if for every a less than b in I, f of a is less than or equal to f of b. Again, here's our interval I, and we would say that our function is decreasing, looks like it's going down, if for every set of points in that interval, any point a and b that we select, where a is less than b, the output f of a is greater than or equal to the output f of b. So technically, both of the functions that I just drew were actually strictly increasing or decreasing, decreasing over the highlighted interval. And it's called strictly increasing or decreasing if there's no equality. In other words, if, as here, f of a is strictly less than f of b for all a and b in that interval, and f of a is strictly greater than f of b for every a and b in that interval where a is less than b. And it's strictly increasing if there's no equality there. So technically, it's sort of strange, but a function like the constant function, x equals 3, technically by the definition, this is both increasing and decreasing, technically, by the definition, because for every a and b, f of a is equal to f of b, so that fits both definitions, but it's not strictly increasing or decreasing. So it's just a technicality, not really a big deal. So I would like you now to apply those definitions to think about this graph, and also think about what's happening to the derivative as this function is either increasing or decreasing. So for this graph of f of x to the right, over which intervals is f of x increasing? Over which intervals is f of x decreasing? Is f prime of negative 3, the derivative at negative 3, positive or negative? Now just estimate this based on the slope of the tangent line to f at x equals negative 3. And is f prime of 2 positive or negative, the derivative of f at x equals 2? Again, using the slope of the tangent line to approximate this. Does f of x have any local maxes or mins? Any absolute maxes or mins? And if so, list them. So I would like you to pause and think about each of these, and we'll talk about it just in a moment. All right, over which intervals is f of x increasing? So we see that f of x is increasing here, and it's also increasing about there. So f of x is increasing over those parts. Now when we say what intervals, what we mean is what values for x. So it appears that this is maybe ending at, I don't know, maybe that's like negative 1.2 or something. This is just estimating, and maybe this is starting again at something like, looks like maybe 3. So over what intervals? That would be the interval from negative infinity up to negative 1.2, as well as the interval from 3 to infinity. Those are the intervals over which f of x is increasing. What about where is f of x decreasing? So it's just decreasing over that part in the middle from here to here. So maybe so it looks like that. According to us, it's everywhere else. That would be from negative 1.2 up to positive 3. Note that these are all open. These are all parentheses, meaning open. So this is neither increasing nor decreasing at negative 1.2 or x equals 3. It is increasing from negative infinity, so this is negative infinity less than x, which is strictly less than negative 1.2. We're not saying what's happening to x at the points negative 1.2 and positive 3. All right, is f of negative 3 positive or negative? So for this, we're looking at the slope of the tangent line to the curve at x equals negative 3. What does the slope of the tangent line to the curve look like? Well, we see that that's a positive slope because for every, units that we're going up in x, we're going up units in y. So that is a positive slope, and that therefore the derivative at x equals negative 3 is positive. F prime of negative 3 is greater than 0. Is f prime of positive 2 positive or negative? So we're looking again at the slope of the tangent line to the curve at that point. So we're drawing the slope of the tangent line to the curve at that point, and we see that that is negative. When we go to the right in x, we are going down in y. And so this is negative. And so f prime of positive 2 is less than 0. Does f of x have any local maxes or mins? Yes, it does look like it has some maxes and mins. So let's see, new color, green. So this right here is a local maximum. This right here is a local maximum, and so that's x equals negative 1.2. Negative 1.2, comma, I don't know what the output is. Maybe it's like negative 0.7. And the other one is here. So this is a local minimum. And that local minimum is, well, my x value is 3, and my y value, maybe that's like negative 3.6 or something. Okay, so the x value is what I'm particularly interested in. So is there anything to note here? Yeah, one thing to note is that we saw that the function was increasing up until negative 1.2 and then decreasing. That's also where our local maximum is. So this negative 1.2, the function was increasing up until x equals negative 1.2 and then decreasing. This local max of 3, what was happening? The function was decreasing and then increasing. So, okay, that makes sense. What else should we know? Oh, okay, we were also asked if there were any absolute maxes and mins. The answer there is no. We do not see any absolute maxes or mins. No, because, for example, this is relative, but not absolute, because there are values less than it appears, like this keeps going down. So there's going to be values that are smaller than the output there. And again, the other one is also relative, not absolute, because f of x gets larger than the output here. So neither of those 2 points are absolute maxes and mins, and we do not see any absolute maxes and mins on this graph. It looks as though it's going to keep going on and on to negative infinity and positive infinity. So there's no one single output that is greater than all of the outputs or smaller than all of the outputs. Now, what can we notice about when the derivative is positive or negative and the situations where f of x is increasing or decreasing? So over like all these, let's say green pieces where the derivative is where the function is increasing. So over this whole interval right here, the function is increasing. And over this whole interval over here, the function is increasing. What's happening to the derivative at each of those points? At any of those points, notice that the slope is going to be positive, right? So the slope is positive if we look at the slope of the tangent line to any of the points where the function is increasing, the derivative is greater than 0. So over all of these places where the function is increasing, f prime of x is greater than 0. What about when f of x is decreasing? So over all the places where f of x is decreasing, basically that's just that red interval in here, for all those places, the slope of the tangent line is going to be negative. F prime of x is going to be less than 0. So this is a really important idea that I want you to both understand and remember, that for a general function f of x, if the derivative f prime of x is negative over an interval, then f of x is decreasing over that interval. And if f prime of x is positive over an interval, then f of x is increasing over that interval. So this is really important, this connection between increasing and decreasing functions and the derivative. So negative derivative, decreasing original function, positive derivative, increasing original function. The second big takeaway I want you to have from these observations is that the connection between when a function is increasing and decreasing, or when the function has a positive or negative derivative, and where local maxes and mins or relative maxes and mins occur. So remember in our example we saw that f was increasing over this interval and increasing over this interval, and that it was decreasing over this interval in here. And we said that we thought maybe it was increasing up until negative 1.2. So we said, let's see, we said here's negative 1.2, where it's increasing up until that point and decreasing afterwards, and it's decreasing until positive 3, that it's decreasing until that point and then increasing again afterwards. What else did we say? Again, the derivative was positive before negative 1.2. It was negative between negative 1.2 and positive 3, and the derivative was positive again for x greater than 3. So just to be very clear, over the interval from negative 1.2 to positive 3, f prime of x is less than 0. And then over the interval from for x less than negative 1.2, f prime of x is greater than 0. And over this interval as well, f prime of x is greater than 0. Okay, how does that relate to our maxes and mins? Well, if the function is increasing and then decreasing, increasing and then decreasing, then what is going to happen at the top? What's going to happen at the top of that hill after it's been increasing and then it starts to decrease? Well, that is a relative max. So that's a relative max. And so if f prime of x is greater than 0 for x less than c, and f prime of x is less than 0 for x greater than c, like we see in this particular case, then c, f of c, that point is a relative maximum. If f prime of c is less than 0 for x less than c, and f prime of x is greater than 0 for x greater than c, then that point in the middle is a relative minimum, as we see over here. So it was, the derivative was negative, and then the derivative is positive again. That point c, f of c right here is a relative minimum. So again, I'd like you to both understand and remember these key ideas as well. The connection between the first derivative, where the function is increasing and decreasing, and where relative maxes and relative mins occur. So putting all those ideas together gives us the first derivative test. It says that to find intervals where f of x is increasing or decreasing, and to find relative maximums and minimums, we can first find the derivative, then find all critical numbers in the domain of f of x. Remember that the domain of f of x is the set of input values that give an output for f of x, the set of values such that f of x is defined. And the critical numbers are the places where either f prime of x equals 0 or f prime of x is not defined, but f of x is defined. So the places where f prime of x is 0 or f prime of x does not exist. Those are the critical numbers. We then make a number line and label all critical numbers and discontinuities of f of x. So we're making a number line, and we are going to say, okay, here is a critical number, here's another critical number, and so on, and also places where the function is discontinuous, because these are the places where the function could change from being increasing to being decreasing. We are then going to test whether the derivative is positive or negative for the values between critical numbers and discontinuities. So we're going to pick points to test and determine, is f prime of x positive or negative? And these are points in between our critical values or places where the function is discontinuous. So we are testing some point in between each set of those values. And as we saw above, if f prime of x is positive over an interval, then the function is increasing over that interval. If f prime of x is negative over an interval, then the function is decreasing over that interval. Next, we find the relative maxes and mins. If c is a critical value, then if f prime of x is greater than 0 before c, and f prime of x is less than 0 after c, that means that the point c, f of c, is a relative maximum. Again, that's just was going up and then going down, positive derivative, then negative derivative. So that on the top of the hill is a relative max. If f prime of x is less than 0 for x less than c, so negative derivative, negative slope, and then greater than 0 after the point c, positive derivative, positive slope, then that point c, f of c, is a relative minimum. So let's do an example. Let's use f of x equals x cubed minus 2x squared plus x minus 2. And first we want to find the domain, the set of input values that for which the function is defined. Then determine the intervals over which f of x is increasing or decreasing. And finally, find all relative maxes and mins for f of x. So we're going to use the first derivative test above to do parts 2 and 3. So I'd like you to pause and try that out, and we'll talk about it in a moment. Okay, so the first part for this problem is pretty straightforward. The domain is the set of all input values for this function. Note that this is a polynomial, and because it's a polynomial, that means it's defined for all possible values of x. F of whatever number you want to plug in, you get a number out. There are no problems. So the domain is all real numbers, or the domain is the interval from negative infinity up to positive infinity. Okay, determine the intervals over which f of x is increasing or decreasing. So first, we want to find f prime of x. The derivative, in this case, we just need to use power rule. So 3x squared minus 4x plus 1 is our derivative for that function. Now we need to find the critical numbers or the critical values, the places where f prime of x equals 0. Note that f prime of x is always defined, that this is again just a polynomial, so there aren't going to be any places where f prime of x does not exist. We just now need to find places where f prime of x equals 0. So we can set 3x squared minus 4x plus 1 equal to 0. Let's see, does this factor? If it does, it's 3x plus or minus something times x plus or minus something to get that 3x squared. And yeah, if we do a -1 and a -1, then this does factor because 3x times -1 is -3x, minus an x is -4x, and then the outer term, the last terms multiply to give us a +1. So yeah, that factors in that way. And now we've got, okay, this means 3x equals 1, so x equals 1/3, and the other critical value, x is equal to 1. These are our two critical values or critical numbers, places where the function is, where the derivative is equal to 0. All right, now we're going to make a number line where we include all places that are either critical numbers, so we've got 1/3 and +1, and we also include any places where the function is discontinuous. There are no such values, so we've made that number line. And now we are going to test points in the intervals between these to see if f prime of x is greater than 0 or f prime of x is less than 0 over these intervals. So we can pick, in general, pick the easiest points you can that are between these values and not actually equal to these values. So 0 is an easy number. Let's say 2 is an easy number. And then we need some number in between 1/3 and 1. I'll use, I'm going to use 2/3 because I'll use 1/2. I'll use 1/2, doesn't really matter. Okay, so I need to test those three numbers and see if the derivative is positive or negative. So my derivative again was f of x equals 3x squared minus 4x plus 1. Let's plug in that's my derivative. And so f prime of 0 is 0 minus 0 plus 1. That is positive. So this is positive. What about f prime of 1/2? That is, so in between 1/3 and 1, in between 1/3 and 1, I'm plugging in f prime of 1/2. That is 3 times 1/2 squared minus 4 times 1/2 plus 1. So that gives me 3 times 1/4. Minus 4 times 1/2 is 2 plus 1. That's negative 2 plus 1 is negative 1 plus 3/4. So that is less than 0. I don't really care about the exact value. All I need to know is it positive or negative? And lastly, f prime of 2 is 3 times 2 squared minus 4 times 2 plus 1, and that's going to give me 3 times 4 is 12 minus 8 plus 1, and that is greater than 0. So this is positive over here. So because I know the derivative is positive before x equals 1/3, that means that the function is increasing over this interval, decreasing here where the derivative is negative, and increasing here where the derivative is positive. And as we've seen, this derivative can only change sign if either there is a critical value, a place where there's a relative max or relative min, or could be a relative max or relative min, or if the function is not continuous at a particular point. And that's why we're interested in the domain of the original function. We're interested in places where the function might break off and change at some points. So what we see now is that based on this, f is increasing where, again, the derivative is positive, so over the intervals from negative infinity up to negative 1/3, as well as the interval from 1 to infinity, and it's decreasing over that interval in the middle. It's decreasing over the interval from 1/3 up to 1. So we've answered our first question. We are not all the way through the first derivative test. The first derivative test gives us both increasing and decreasing intervals, and also lets us know relative maxes and mins, local maxes and mins. So we also need to find that. So part 5 of the first derivative test said that if c is a critical value, if f prime of c is greater than 0 for x less than c, and f prime of x is less than 0 for x greater than c, so in other words, the derivative is increasing, then the derivative is decreasing, then f of c is a relative max, and similarly, if the derivative is negative, the function is decreasing, and then the derivative is positive, the function is increasing, then that's a relative min. So we can use that number line that we found above to find all relative maxes and mins for f of x. So based on our number line, because the derivative was increasing up to 1/3, that means, and then decreasing afterwards, that means 1/3 comma f of 1/3 is going to be a relative max because we were increasing and then decreasing. And 1 comma f of 1 is going to be a relative min because, again, we were decreasing and then increasing. Our derivative was negative and then our derivative was positive. So to find all those points, we just need to plug it into the original function. F of 1/3 would give us 1/3 cubed minus 2 times 1/3 squared plus x minus 2. So that's 1/27 minus 2/9 plus, that was a 1/3, sorry, plus 1/3 minus 2. And then we can simplify that. And we could get a common denominator there and find an exact fractional answer, but I'm just going to use a calculator to simplify to get negative 1.85 as that value. So we have 1/3 comma negative 1.85 is a relative max. So that's a relative maximum. And f of 1 we would have 1 cubed minus 2 times 1 squared plus 1 minus 2. So that's 1 minus 2 plus 1 minus 2. And that would give us a negative 2 when we simplify that. So we've got 1 comma negative 2 is a relative minimum.